Next, I wanted to give you a quick overview of the Finding Zeros of Polynomials set of notes. Remember that I don't expect that these little summary videos are going to be a replacement for reading the notes and looking over the examples. I just wanted to give you sort of a quick overview of all of the stuff that I think is important in the notes, but I still expect you to read over the notes carefully and then look over the examples videos before you'll fully understand it. So there's one thing that I wanted to mention before we talk about the first theorem in this set of notes, which is that there's a property of the degree that's a little bit important when it comes to graphing, or at least it's important as sort of a sanity check that your graph is reasonable. So this is the polynomial that we graphed in the last overview video. Notice that the degree here is 3. Now, the degree tells you the most number of roots that a polynomial can have, and it also tells you, one smaller than the degree is the most number of turnarounds that the graph can have. So in this case, because the degree is 3, there can be at most 3 roots and at most 2 turnarounds. And we saw already that this is the graph of this particular polynomial. And it does indeed have 2 turnarounds. So there's a turnaround here and there's a turnaround here. So this graph does have the maximal number of turnarounds. It does also, in a sense, have 3 roots because the root at -1 is repeated with multiplicity. But if you'd like to think of this as just being 2 roots, then that's also totally fine. The point is just that 3 is the maximum number of roots that we could possibly have. So if you were trying to draw this polynomial and you ended up crossing the x-axis 4 times, you would know that something had gone wrong, because the degree limits the number of roots that a polynomial can have. So we've already seen that our general strategy for graphing is to identify the roots and the root behavior at each of those points, and then we can connect all of that into a big graph. And you'll see several, I guess you already saw several examples of that in the last video. But now let's look at some other theorems that we can use to help us identify some of these zeros. So because our general graphing strategy relies on finding zeros and their behavior, we're going to look at some extra tools that we can use to find those zeros. So the first tool that we're going to use is called the rational root theorem. What it says is that if you are given a polynomial that looks like this, so here an is the leading coefficient and a0 is the constant that shows up at the end. If all of these coefficients are integers, then you can apply the rational root theorem, and that just says that the only candidates that you should have for rational roots are going to be plus or minus the factors of a0, which is the constant term, divided by the factors of your leading coefficient. So this gives us a complete list of all of the numbers that we should try plugging in as possible candidates for roots. So let me show you just a hands-on example involving this. So let's look at this particular polynomial. So here the leading coefficient is 1, and the constant coefficient is a -2. And because all of these coefficients are integers, we can apply the rational root theorem, which says that all of the candidates that we should have for rational roots are plus or minus the factors of a0 divided by the factors of an. So let's look at the factors for each of these. The factors for 2 are 1 and 2, and then the factors for 1 are just 1. That's the only factor for 1. And the rational root theorem says that the only candidates that we have for rational roots are going to be plus or minus the factors of a0 divided by the factors of an. So in this case, we have, maybe I'll do the factor 1 first. So that's the first factor of a0 divided by the first factor of an. Or we could have plus or minus the second factor of a0 divided by the factor of an. So any combination of these could be the candidates, and then you can simplify these. So plus or minus 1 are a few candidates, and then plus or minus 2 are also candidates. Now, these are the candidates that we would then plug into this polynomial up here to see if they are roots. So not all of these will be roots, but these are the only rational candidates for roots. And if you were to plug these in, usually we'll do this step with a calculator just to speed things along, but if you were to plug these in, you would find two roots. One root of this expression is a positive 1, and then another root of this expression is a negative 2. And now that you've found all of the roots, we can use that to factor the polynomial like we did in the previous video. If you were to do that, then what you would get is f of x is equal to x minus 1 times x plus 2, because those are the linear factors that have the roots 1 and negative 2. So this gives us a way of quickly identifying the roots of a polynomial and then factoring it. We really only need one of the roots in order to start factoring. For example, if we knew that this was a root, we would then know that f of x was divisible by x minus 1, so we could divide out that factor and find the other factor to be x plus 2. So that's where the rational root theorem can come in handy. The next theorem that you're going to see in this set of notes is called Descartes' rule of signs. The statement is kind of complicated, but I think applying the theorem is a little bit more straightforward. So Descartes' rule of signs says that the number of positive real roots that a polynomial has will be the number of coefficient sign changes in that polynomial, or it will be less than that by an even number. And similarly, the number of negative real roots that a polynomial has will be the number of coefficient sign changes in f of negative x, or less than that by an even number. So I think instead of worrying too much about the statement, let me show you what I mean by this. Let's first just look at the number of positive real roots that this polynomial down here has. This is the one that we looked at in the last summary video, so we've already seen how to graph this polynomial. But let's look at the number of coefficient sign changes. So what I mean by that is let's look at the signs for these coefficients. So the signs are a positive 1, a positive 1, a negative 1, and a negative 1. So you look at these from left to right. I mean, it doesn't matter if you go left to right or right to left. You're just looking at the number of times that the sign changes as you go from one side to the other. So in this case, we go from a positive to a negative. So this would be one sign change, and then we stay negative. So there's one sign change between all of these coefficients as we go from, let's say, the left side to the right side. So that's what I'm going to call the number of coefficient sign changes. And what Descartes' rule of signs says is that the number of positive real roots that this polynomial has is going to be that number or less than that number by an even number. So it would either be 1 or a negative 1 or a negative 3 and so on, but you can't have a negative number of roots. So in this case, we know that this will have one positive real root. And indeed it does. We already found the roots. We know that positive 1 is its only positive real root. And we can do the same thing if we're looking for negative real roots. We would plug in negative x into this polynomial. So that would be a negative x cubed plus a negative x squared minus a negative x minus a 1. And then if you simplify this, this would be a negative x cubed plus an x squared plus an x minus a 1. And now, now we can look for the number of sign changes in f of negative x. So this coefficient is negative and then positive, so that's one sign change, and then positive and then negative. So here's a second sign change. So we go from negative to positives to negative. So there are two sign changes in total. And that means that the number of negative real roots is either 0 or 2. Because remember, the number of negative real roots is either the number of coefficient sign changes or less than that by an even number. So there are either 2 or less than that by an even number, so it could be 0, negative 2, negative 4, and so on. We can't have negative numbers of roots, so there are either 2 or 0 negative real roots. So this theorem is mainly useful whenever you just want to know whether you're done finding positive real roots or done finding negative real roots. In this case, there are actually two negative real roots because we know that negative 1 is a root with multiplicity 2. So that's a way of identifying how many positive real roots or negative real roots there are. And then the last theorem that we're going to look at in this set of notes is called the linear factor theorem. All that this says is that if you allow complex numbers in your factorization, then every polynomial of degree n can be factored as a product of these n linear factors. So x minus the first root times x minus the second root, and so on, all the way down to the nth root. And then this a out here is, as usual, the lead coefficient. So let's just look at a quick example of that. All that this theorem is saying is that every polynomial can be fully factored if you're willing to write in some complex numbers. So here, if I were to factor out a 7, which is the lead coefficient, what I'd be left with is an x squared plus 1. Now, x squared plus 1 is supposed to factor as x minus its first root times x minus its second root. We know that the roots of this expression are plus or minus I. So we know that this can be factored as x minus I times x plus I. And this is just confirming the statement in this linear factor theorem for this particular polynomial. It just says that you can fully factor any polynomial as long as you're willing to write down some complex roots on the inside. So this polynomial doesn't have any real roots, but it does have these two separate complex roots, each of them with multiplicity 1. So you'll see the applications of these theorems. Again, I don't expect that you immediately understand all of these theorems. I think you'll need to see several examples for that. And I also want you to read carefully over your notes. There are some typed up examples there. But I think it might be useful to you to just have a big summary video at the beginning that you can